Okay, so we'll get started again. Remember, you will not remember everything in this section. No pun intended. This is not taught in medical school or dental school or nursing school or pharmacy school, whatever. It's not taught in any university. I know because, like many of you here, I've gone through that process. But you're going to question why it's not taught by the time I reach the end. And please stop me at any point if you've lost me. Because if you have, you're just going to get more and more confused as time goes on. So I'm telling you, do stop me. It's not a problem. I get people learn in different ways. It's not an issue. That's why we're here. So again, we'll start simple and build up. It may seem too simple at times, like at the start of the day, but it's so that by the time we get to the end, everyone gets everything. It's for a reason. What's this? Someone says Krebs cycle? Glycolysis. As a rough rule, if Rich says it, it's probably correct, okay? This is glycolysis. We are taking the glucose, which has come from branches of it in what we're eating, and broken it down into individual pieces of glucose, 6 carbons, and then we end up with this thing, 2 pyruvates, each of 3 carbons. You don't have to be familiar with all of this, but look at this. Again, you don't have to be familiar with the nuances. I just want you to see that the word NAD is there. It's involved. But it's not NAD, it's reduced NAD. NAD plus and NADH are 2 different things. NAD plus is a boat. And all you do is you load the boat at the dock with some hydrogen, and it takes it to the other side of the dock, goes from Dover to Calais, and the hydrogen is unloaded and used over there. All NAD plus does is transport hydrogen. That's the only point of it. Turn that on silent, sorry. There we go. And so it's used. It's actually used, ATP is used, etc., blah, 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 but glucose to pyruvate. Now, what's this, apart from Rich? Sylvie, you spent enough time with him? This is beta-oxidation. Yeah? This is how we take fats and turn it into the same ultimately. I know it looks different because glucose went to pyruvate and this is going to acetyl-CoA, but what happens if you put them side by side? So the glucose only makes pyruvate so that the pyruvate can get converted into acetyl-CoA as well. So regardless of what you put in your mouth, the body is trying to get to this. Acetyl-CoA. That's all it wants. That is the thing that enters the process to create ATP, which is the energy currency. If I say ATP, are you all familiar? Yeah? Okay, good. However, now it gets much more complex. Like I said, I want you to understand as we go along, and that's enough. You don't have to remember. Like I said, what I'm about to show you, I've been studying for 6 years and I still learn something new every time I look at it because it is so complex. But we will break it down, don't worry. So, what am I going to talk about? Anyone want to tell me? Eventually, yes. Before we get to that, yeah. This is where we're going to see that thing that I said was the most important when it comes to NAD, the Randle cycle. Yeah. And when we go through it, you'll think, why the hell is this not taught at university? Why the hell do people that make our laws around food not know this stuff? I've taught this to people with PhDs in the subject, and they've sat there racking their brain. That doesn't mean it's going to be even more difficult for you. They're racking their brain because they cannot believe everything they've learned up to that point is completely in opposition to what's empirically observable. And it is observed. This isn't an opinion. This is happening in all of you right now, to some extent. And if you don't get it, it's fine, because you will get it eventually. And we are going to break it down into simple terms in terms of headlines at the end, after we go through the subtle nuances. But if you don't get what it's representing, which will be very simple at the end, then you cannot plan NAD. And you'll understand why very, very clearly. So we'll go through it slow. I've got a whiteboard here. I'm notorious for filling up whiteboards, as you know. So we'll go through it bit by bit. So when we have fats, we eat them. It goes into the cell. So this represents the edge of the cell. The fat has entered the cell. Then this is the mitochondrion. It looks a bit like a kidney bean, I guess, or a kidney. The mitochondrion doesn't have an edge at the edge of the cell. It has two edges. So this brown, dark brown border, there's a section where it touches the white of the slide and where it touches the beige of the inside. So it has two edges, or two membranes, an outer and an inner. And the inside of the mitochondrion here is where all the cool stuff happens. All of this stuff here, which I know looks ridiculous, but it will make perfect sense. So the fat enters the mitochondrion, i.e. it enters the cell, that's the cell membrane, and then eventually it goes into the mitochondrion. And it's going there ultimately to be turned into acetyl-CoA, which is here. Remember, glucose enters the cell, and that's the GLUT4 that we mentioned before. If the cell is able to present GLUT4 to the surface, if is a big word here, think about how many people have diabetes, then glucose comes in. That entry there is this entry here. And glucose gets converted to the pyruvate, as we said, so that the pyruvate can enter the mitochondrion and turn into acetyl-CoA. So simple terms, glucose turns into acetyl-CoA, fats turn into acetyl-CoA. Summary. Then we get to the bit which is not taught. I don't know why. When the fat enters the mitochondrion to be metabolized, the fat here is turned into acetyl-CoA there, and that acetyl-CoA is this here. So it's just the same thing happening but in parallel diagrams. This is simplified. Obviously this is with a bit of geography. So the acetyl-CoA is there. The fat is in the mitochondrion here, and then it turns into this. When it turns into acetyl-CoA, that gets converted into citrate. Hence why this is called the citric acid cycle, or the citrate cycle, Krebs cycle, tricarboxylic acid cycle, or the same thing. I mean, just people like to be complicated to make them sound so clever, so everything has weird names. That acetyl-CoA converts to that citrate there. Again, summary, fat enters the cell, enters the mitochondrion, turns into acetyl-CoA, turns into citrate. That citrate will build up inside the mitochondrial matrix. And when it builds up, you have more of it in here than out there. And you move down the concentration gradient. So if I take a puddle of water and drop a dry sponge, there's more water outside the sponge than inside. It goes from area of high concentration to low concentration down the concentration gradient. So it's not just with water, it's with anything, any kind of ion. Citrate here is basically an ion. That's why it's called citrate and not citric acid. So the citrate builds up, and that's how it can move out back into the main part of the cell. So that citrate there is the same as there, but it's just shifted. And that's the parallel between the diagrams, the movement. So what happens once it goes from there to here? Pay attention. It blocks the action of other stuff. So this citrate, as a result of fatty acid catabolism, is blocking, number one, this thing here. It's not just damage to the mitochondrion that blocks glucose entry. It's not just having enough energy that blocks glucose entry. It's the burning of fat that blocks the GLUT4 receptor there. Remember, first question, what are you eating? So this citrate here blocks glucose entry. It also blocks, remember that green diagram with the green circles at the top and the green circles at the bottom, glucose to pyruvate? It blocks portions of that process to turn glucose to pyruvate. So those two parallel with these. Now, technically, this should also have a dotted red line going here. So its glucose is now blockaded to some extent at the entry, at the conversion of fructose 6-phosphate to fructose 1,6-bisphosphate, technically it should be, and also the conversion of phosphophenol pyruvate, PEP, into pyruvate, if you want to be technical. So it blocks that. As well as that, the acetyl-CoA that's made here blocks this enzyme, PDH, pyruvate dehydrogenase, and it prevents the pyruvate from glucose and other places converting into acetyl-CoA if there's too much. So go down here, citrate builds up, moves out, and then that blocks other stuff. So if we bring the original diagram back, that's what we're saying. This fat to acetyl-CoA to citrate, that moves out, blocks glucose in multiple points. And again, this is measurable. It's not an opinion. You can see this happening if you look for it. And if we go back, what is, for the context of today, the most important difference on this diagram between the way we go from glucose to acetyl-CoA to fats to acetyl-CoA? I'll be very impressed if anyone gets this. So the answer is this. What's FAD? We're here for an NAD course, but FAD is flavin adenine dinucleotide. It always gets forgotten. But if you don't look at that, I'm sorry, but you haven't got a clue what you're doing when it comes to planning NAD. They are there at the same time, right next to each other for a reason. Not just in this, but in other things as well. When you burn glucose, you're not producing this stuff. When you burn fats, part of the breakdown into acetyl-CoA produces FAD2H. That has a big part to play. When the fat comes into the cell, here, and then moves into the mitochondrion, here, it doesn't just make this, it produces this. So time for the whiteboard. So I'm going to write out that equation there. Can everyone see this? Okay. The enzyme in green there succinate dehydrogenase. Dehydrogenase dehydrogenates, takes the hydrogen off, hence why the FAD is gaining hydrogens. Anytime you see a dehydrogenase in a metabolic pathway like this, or this, a DH there, or a DH here, taking hydrogen away, probably FAD or NAD is involved to go to FADH2 or NADH. That's the whole point. Remember, NAD is a boat that carries hydrogen across the river so hydrogen can go to where it needs to be. That's the whole point. That's why we have dehydrogenase enzymes to load the boat. And that then goes off and does what it needs to do. But here's a concept you need to understand now. And again, you need to stop me if you're not with me. In chemistry, we have something called Le Chatelier's principle. God, that's a crap pen, isn't it? Oh, that's much better. Anyone want to tell me what Le Chatelier's principle is? Okay. Any chemical reaction that is reversible has what's called a Kc or a Keq, which is called an equilibrium constant. You think, because of the nature of the way we think, in a reaction like this, you've got, in a mixture, let's say that's in a glass of water or something, some mixture, you immediately think, well, half of it's that and half of it's that. Not the case. Remember glucose in the linear form and the circular form? Hence why we went through that at the start of the day. I said most of glucose is in the circular form, the ring form. Some of it is still in the linear form. In order to start the Maillard reaction, Amador rearrangement, ketoaldosamine, blah, 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 you get the glycation, protein function loss, ultimately cell death. How far or how much of this and this is called the equilibrium constant? If the equilibrium constant is above halfway, you get slightly more of this than that at equilibrium. Le Chatelier's principle states, if an equilibrium experiences stress that shifts the equilibrium will shift to reduce the stress. So if we have that 50-50, let's say the equilibrium constant here is, in layman's terms, 50%. And in the mixture we add a load of B, that B gets converted to A and it goes back to 50%. Not too complicated to understand, I hope. All that's different now is you've got more of each. That's all. But sometimes the equilibrium is over here, sometimes it's over there, sometimes it's almost all on one end, sometimes it's perfectly in the middle, blah, blah, blah. What do you notice about this reaction here where FAD comes in? That arrow has two ends. When we are burning fat, we are adding this, so what does the equation do? It goes the other way. That goes in reverse. Because that builds up and it equalizes to some extent the equilibrium, so it goes backwards. Adding more of this doesn't mean it carries on going forward. It actually goes backwards. So it maintains the equilibrium constant of the reaction. That's why that being produced is one of the sources of the Randle cycle's existence. The fact that fat produces FADH2, whereas with glucose you don't necessarily do that. That then triggers so many other differences as you go forward. Everyone understand this and the parallel? Okay. Now, that's why, as we burn the fat, FADH2 slows down the conversion of this, the fumarate, all the way around to isocitrate. Half the Krebs cycle. It's not shut down, because you die if that happened, but it's greatly, greatly affected. So all of those are reduced now in production. So how then do we get back to this to carry on? And that's the key. Well, remember, that citrate builds up as we keep converting the acetyl-CoA, and that goes to this. Because the acetyl-CoA to citrate, remember, there's not a double-handed arrow. That is what we call thermodynamically feasible. So it just happens. And therefore, the citrate just builds up. And because we make more NADH from fat as well, hence why you can run longer on fat than glucose, by the way, because there's more energy available, you get more isocitrates built up. And the reason comes back to this. We're making more NADH from fat. Look at this here. The NADH is there. So if we increase that, can you all see, by the way? So if we increase this NADH, it sends it the other way. Just like if we increase the FADH2, it goes backwards. So we're increasing the NADH because that's produced more in fat. So it goes back to this. So then the isocitrate builds up. And the isocitrate, that's got a reversible reaction now to citrate, another A to B. So the isocitrate is B and citrate is A. So now the isocitrate increases and it shifts over here to rebalance. So then the citrate builds up. When the citrate builds up, just like when you're cooking, well, I don't cook, but if you were to, I've seen my mum cook, on what's the thing where the steam comes out? What's it called? No, there's like a thing, when you put, that's the one, yeah. Right. I'm so removed from reality. So you have that, when the difference between the pressure inside and the room is big enough, it's so big, it forces itself out, and then you get the whistling sound that I used to hear all the time as a kid. That's the pressure cooker. Was it pressure? Yeah. That's the pressure cooker. When the citrate builds up, it has to go through the pressure release valve. That's why this moves out. And then it blockades the glucose to some extent in certain places. So that moves out. Because the isocitrate builds up, and so the citrate builds up. Then, like I said, the movement. But this mechanism is not a one-way door. This is what's called an antiport mechanism. An antiport mechanism is where, in order for something to go out, something has to come in. It's a swap. What comes in? Well, it's circled, I shouldn't really be asking. So the citrate goes out, and malate then comes in, it's swapped. So then this goes to an up arrow. The malate is restored because the fumarate goes down because we're adding in FADH2 and it pushes it back towards here. But malate can come in, so then that is restored. When the malate is restored, there is a shortcut that they don't teach you even in school in the Krebs cycle. And I know someone in medical school now who keeps posting her metabolism stuff, and I'm messaging her saying they're not teaching her everything. She thinks I'm mad, but the malate can go straight to alpha-ketoglutarate. There's something called the malate-aspartate shuttle, where there's a few enzymatic steps involved, which we don't need to know for NAD purposes, but the malate shortcuts across to alpha-ketoglutarate, and then it goes around like this. And then even the fumarate is restored, because as it goes around, FAD is used, and it rebalances, and then you go this way. It's no longer a circle, it's like a wedge or whatever shape that's called. And that's what happens when you burn fat. That's actually the Krebs cycle for fats, which directly inhibits the utilization of glucose. But we have to flip things on its head. By the way, do you get NAD now? What it's used in? It's such a small part. And there's so many things that allow NAD to have any function at all, that if you don't ask your patient those things, or yourself, or whoever you're using it with, you're wasting everybody's time. Even if you mean well, you do things wrong. In the past 6 months, I've probably had three people hospitalized because the person looking after that patient didn't bother to look into things in detail, which unfortunately is not their fault. I don't blame them because no one teaches it. Hence why I decided I was going to start teaching it. But that's fat. What happens if we go down this pathway and we use glucose instead? Whoops. When we use glucose, it just goes around like that, and that's what we're taught. Because we're taught when we're in school, you need glucose for energy, which, as we've already seen, is complete rubbish because we get more ADH from fats rather than glucose. But what happens here is the acetyl-CoA comes in and it goes round, and that citrate eventually comes out of the cell again, there, and gets converted into malonyl-CoA. That has an inhibitory effect on the fat burning now. So the fat, if you look at this CPT1, carnitine palmitoyl transferase 1, that enzyme, when the fat comes into the cell here, it drifts down, and then it crosses into the mitochondrion. That crossing in is that enzyme, carnitine palmitoyl transferase 1. That's why people say take carnitine if you want to burn fat. It's because it's what gets it into the mitochondrion. But it's bullshit, because even if you take carnitine, how do you know whether you're actually going to burn the fat if you don't control the inhibitory process on the fat burning? They never mention that. So if that is blockading this, then the glucose is burnt and it goes around this way. And there's if that's happening, it will just keep on doing that. If this is happening, it will just keep on doing that. There's a level of inertia because of the presence of something known as an equilibrium constant. Once the equilibrium is in a particular place, it's very hard to shift out of it because you've got the forces of the universe fighting against you in electromagnetism. And so that's why, if you're going to have a mixed diet, you need at least 3 days, I would say, on one end of the spectrum before you go to the other. And that will make sense later. But eventually, what will happen if you try and mess things up, this entire structure is damaged. That entire structure on its own being damaged blocks this thing here. So it's not just putting too many carbohydrates in your mouth that can cause diabetes. It's too much damage that can block this transporter. Now, sugar may get in other ways. You may not be diabetic, but the pathology has similarities. So what causes that? Well, number one, carbohydrates, glycation, because we lose protein function. Imagine the glycation happens to this thing here, AMP kinase. Well, how are you going to get that in there? If that can't work properly, how can the GLUT4 go to the surface for glucose to go in once insulin docks? You can't. Hence why it protects itself. What happens when you try and go down both sides at the same time? The glycolysis pathway and the fatty acid beta-oxidation. Yeah. You're going to have a lot of problems, basically, in layman terms. But, you know, you've got oxaloacetate being reduced in concentration when we go down the fatty acid pathway, and we've got it normal or increased relatively in the glycolysis pathway. If you try and go down both pathways at the same time, what's going to happen? How can it go up and down at the same time? In order for, let's say you've got a road here, and you've got both lanes going past each other. If there's roadworks happening on one side, they block the cars coming here, and then they carry on. And then they block them, and these guys carry on. Imagine they try and let both flow lines of traffic go at the same time. It's going to be people mounting the curb. They'll get through eventually, but there'll be so much chaos and problems, people with dents and whatever, as they try to make their way past each other, you're going to get serious issues. That analogy is the same as this. And again, it's not an opinion. This is observable. the shortcut from malate to aspartate, it takes advantage of something like this, a glutamine transport on one of the SLCTs. And then you go around this way as a shortcut. That you can see that if you took a microscope in yourself now. So, here's the takeaway message, even if you end up forgetting the intricacies of what we've just gone through. As a matter of fact of paleobiology, i.e. looking at how we are made, how we exist, we can tell what we are supposed to do and not supposed to do. You either need to be a vegan or a carnivore, according to our own DNA. Why else would one block the other if we can digest both at the same time? This is how you grind your gears. So in other words, complete and utter bullshit is what a balanced diet is. Any bureaucrat that wants to push a poster with a balanced diet, I invite them to debate me on the Randle cycle and prove to me how that has any standing in biochemistry whatsoever. It's complete and utter bullshit. You've seen the blockade for yourself. You can't possibly do both at the same time. How can you increase one intermediary step of the Krebs cycle and decrease it at the same time? It's just not possible. So you have to be either a vegan or a carnivore according to nature, because that's observable. Do you understand now why the first question to ask always is, what are you eating? If you don't ask that, you're wasting everyone's time. By the way, if you put stuff on social media, could you tag me? Because I don't have many followers. Yeah, thank you. So, roughly speaking, it is inherently inflammatory to grind those gears. The inflammation will cause oxidative stress. You saw that diagram with the mitochondrion being damaged and then it blocking glucose entry, etc. The damage to the mitochondria means you can't have as much NAD either. And we talked about aging being, the scratch on the CD, the damage to the DNA. Well, things like free radicals and oxidative stress damage the DNA all the time. Glycation damages DNA, hence why the cell can't let more than a certain amount in if AMP kinase senses that level has been reached. And it has to block more coming in. But then we term it insulin resistance and we tell people your cells aren't working properly. Ridiculous. So that's where NAD fits in. I know we've gone a very, very long-winded way, but if I just said, it's used in metabolism, it means nothing. But you get it now. And now you understand how you plan, how you start to plan NAD, because you look at all those other things. And then if that happens and you get less of this, that's everything. That is utterly everything. We talk about what diseases can we cure with this. Well, what can't you cure? Disease is just, in one sense, loss of cell function. Now, there are multiple sources of cell function, but if that is linked to this, I don't even know how many things we're starting to see reverse with this. But the problem with all of those studies is they just give NAD. Yeah, fine, great. But as you're about to see, that's not how you treat and plan a patient. Number one, it can be dangerous if you get it wrong. And number two, it's not sustainable, as I'll show you very, very clearly. So then once we have that, remember I showed you that metabolic pathway, so we have food in our mouth, ultimately to ATP. ATP isn't created in the Krebs cycle. So what does this gearbox, the gear of glucose and the gear of beta-oxidation, glycolysis and beta-oxidation, what does that, when that is in a gearbox, where does the prop shaft go to the differential and then the wheels to make the car go? That's when this comes in, which Kim said earlier, the electron transport chain. That's that bit there. So the Krebs cycle is loading the boat with hydrogen. there is the boat loaded with hydrogen, and it is going across the river to this foreign land where it's offloading the hydrogen and it can then use it for other stuff. We are now into the nitty-gritty of where NAD is actually used in the body and for what purpose. And it will all make sense now why it's linked to so many different, completely unrelated, seemingly unrelated diseases. That boat is offloading here at the electron transport chain. So this is just a zoomed in version of that. Now remember, I said a cell has a single edge or a single membrane. The mitochondrion has one where the brown touches the white and one where the brown touches the beige. Outside membrane, inside membrane, outer and inner membrane. This is the intermembranal space, and this is the mitochondrial matrix. And in the matrix here is where all this happens. Now I said, when we burn fat, we produce the FAD section here, which is there. Succinate to fumarate. The problem with this picture, it makes it look like that just happens in this matrix. Technically, I mean, it's a good diagram to explain a lot, but technically it's incorrect. What's actually happening is that step is actually part of the membrane. Technically, what you should draw is part of a circle, and then something goes along here in a straight line, and then the circle joins to it. So succinate to fumarate is succinate to fumarate there, on the actual membrane. So the Krebs cycle is partly inside the matrix, partly on the membrane itself. It's a continuum. The cell doesn't care where it happens, it just goes. So then we have the NADs, which we're all here for, and that's used there. Do you see now why you can't talk about NAD without also talking about FAD and then also talking about glucose and fats? Because that's the only way you get this boat over here and you offload. That's the boat docking and then undocking and releasing the passengers onto this here and this here, which are the hydrogens. And then you get this process where electrons are shuttled down here and hydrogens, which are protons, by the way, just those positive parts of the nucleus, again, hence why we started with atoms, and they build up in the intermembranal space. What did I say happens in that? What was that thing you said? What was it the thing with the steam?
Oh, the
Pressure cooker.
Yeah.
What did we say happens when the pressure builds up? It forces its way out. When the pressure builds up here of these protons or hydrogen ions, it has to force its way somewhere. It goes in through here. Now, what was the thing? Yeah, okay, so I forgot this. So when we talk about NAD plus or FAD, you could technically just use one, theoretically, but it's going to be much less efficient. So you need proper production of both in order for it to function. Now, that means we already know fats or carbs are the choice, not fat and carbs. But we've already said that one causes glycation and damages protein function. And we already know, so that represents carnivore, that represents vegan. Everyone knows veganism leads to deficiencies and you have to have infusions. It's not, even a vegan would agree with that. So what do you think our ancestors ate if this is what our DNA is selected for? It doesn't take a genius. And we know that that also causes glycation. Hence why the body in gluconeogenesis will only put an amount of glucose in you that does not lead to excessive damage. If you heat someone up in a pan, they will sweat to reduce their body temperature and bring it back down. If you freeze them, they will shiver to bring it back up. If you add a certain amount of ions into their blood, then they will have carbonate in there, with amphotericity is a technical term, to neutralize that and bring it back down to 7.36 pH. When the body brings it back to something, you don't have to be Albert Einstein to figure out what it's telling you. When you eat carbohydrates and the glucose level goes up and the body pushes it back down, what does that tell you in the same context? It's so intricately linked to NAD. So if you grind your gears and you have that inflammation and you have less NAD, you're also going to have less potentially FAD. So the whole thing drops down. So what does that mean? If the boat isn't going over there, this entire section doesn't happen. And what's happening at the end of the section, anyone? ATP. If any cell in your body wants to do anything at any time for any reason, that's what it spends. That is the US dollar. You have to spend that. It's adenosine, which is a sugar, with 3 phosphates. So you've got $3 you can spend. You spend one, you've only got 2 left. You're from ATP to ADP, try to diphosphate. That's your bank account. You've got £3 in there. So every time that is reduced, the whole cell has less money. So you can't build your business if you've got no resources. And the cell function is lost. And what have we defined disease as for the purpose of today? Things not working properly, the function being lost. This is how I became a carnivore. I didn't know what carnivore was. I just looked at this. After I started eating this way, then I found the carnivore community. It was normally the other way around. I did it in a really weird way, just because I was obsessed with this, trying to figure out. For at least, let's say 5 years-ish, I thought I didn't have a clue what was going on in this, because the conclusion I came up with was, well, you have to eat vegan or carnivore. I didn't call it carnivore back then, but that's what it was. Because carbs and protein is a plant, if you think about it, and fat and protein is an animal, if you think about it. It's only breast milk that has all 3, carbs, proteins, and fats all together. So then I thought, well, you have to eat one way or the other. And I thought, well, that can't be right, because everyone says eat a balanced diet. So I thought my understanding was wrong. And then one day I thought, what if the guidelines are wrong and I'm actually right? And I am. Because that's observable. There's nothing opinionated about it. And then we see this. Find me a carnivore that developed a chronic disease. I'll give you £1 million if you can find one. Carnivores that had one already when they started, that's a different thing entirely. And there's complications from that. But it's very easy to find a vegan that had no health problems, and then they develop them all the time. Vegans that stop getting periods, that become infertile, blah, blah, blah. So find me one carnivore that had that. It's impossible. Because that entire thing, the gears aren't undergoing grinding. So it's inherently anti-inflammatory. It's inherently anti-NAD plus depletion. The first question, remember, always is, what are you eating? If you don't answer that, how are you going to know? Yeah? So the take-home message, everything starts with what we put in our mouths. And depending on what goes in our mouth, we do or we don't get the grinding of our gears, which is then what gives us a depletion of those particular molecules. The NAD+, the FAD, and our hydrogen boats cannot take the hydrogen to the electron transport chain to produce ATP, and therefore we have less function overall in all cells, in our entire body. And then, because of that, we get disease. So long story short, we can shorten it to this. It's not that complex at the end of the day. People say, when you lose NAD, it causes disease. No, nonsense. You get that now. The NAD is the dependent variable. It is downstream to other things. Therefore, it's the other things that bring this down in the middle of this, and then you get the disease. But if you don't know all the Randle cycle stuff I just told you, how are you going to know? And so you're just going to see that going down and then causing disease. So you think, oh, we need to put the NAD back in. No one seems to ask, why is it going down in the first place? Or even, why would it go down to give us disease out of nothing? Why would we be alive today if that's the way the body worked? Every single thing it does is to maximize our chance of survival and replication. So that itself is only downstream. And if you're ever downstream of anything, you have to go upstream to find the source and turn the tap off instead of trying to fix the leak while the tap is still on. So again, the most important thing, what are you eating? Yeah. So this is the analogy when you want to plan NAD for anyone.